All right, today we're going to deconstruct a piece of hardware that's absolutely essential to our modern world. But, most of us never even see it. It's the globe valve. And we're going to take this thing apart piece by piece, right down to its blueprint.
Now, I know, this probably just looks like a heavy chunk of metal, right? But this device, and others just like it, they're basically the gatekeepers of our entire infrastructure. Seriously, they control the flow of everything: water, steam, oil, gas, all moving through the arteries of our civilization. So the big question is, how does this one object have so much power?
So yeah, how does it control all that? Well, to really get it, we've got to start with its most basic job as this unseen flow controller.
Okay, so this thing is called a globe valve, and its whole job is surprisingly simple, really. It's got three main functions: to stop flow, to start flow, and this is the really crucial part, to regulate it, to get the flow just right. The best way to think about it is like a super heavy-duty version of the faucet in your kitchen. You can crank it on full blast, shut it off completely tight, or just let a tiny trickle through. Same idea.
Okay, so that's what it does. But the real mystery is, how? How does just turning a simple wheel on the outside manage to control what could be a really powerful flow on the inside? Let's dive in and find out.
To figure that out, we've got to look inside. So let's break down the anatomy of this valve.
And there it is. This is a cross-section, and it shows us all the guts, all the internal moving parts. Now, it might look a little complicated at first glance, but the principle behind how it works is actually, it's beautifully simple.
It really boils down to a simple four-step process. First, you turn the hand wheel. As you do that, the central stem starts to rise. That stem then lifts the disc off of its seat, which opens up a path, and boom, just like that, the fluid flows through. It's just a simple but really powerful mechanical action.
So let's break down those key parts we just mentioned. First up, you've got the hand wheel. This is basically the user's control point, the human interface. It's where an operator grabs on and applies force to get the whole thing started.
So that hand wheel you see is connected directly to the stem, and it's a really simple but kind of ingenious design when you think about it. All that spinning, rotational force you apply to the wheel gets translated into the straight up and down motion of the stem.
Okay, now for what is arguably the most important part inside: the disc. The easiest way to think of this is as the plug. It's the part that moves up and down with the stem to either completely block the opening or let fluid pass through. This little component right here is truly the heart of the valve.
So you see, the disc sits right in the middle of the flow path, and it's all housed inside the main body of the valve. When that disc is lowered, it presses down and creates a perfect seal, stopping everything in its tracks. But when it lifts up, the path is totally clear. This is where all the real control happens.
Okay, so now we get how it works mechanically, right? But you might be wondering, how do engineers know what this thing is actually made of? Or, how much it can handle? For that, we've got to learn how to decode the technical spec sheet.
Right away, the blueprint gives us our first big clue about its construction. It says the principal material is gunmetal. But here's the thing, a valve isn't just made of one single material. The mix of materials is absolutely critical to how it functions. Yeah, a valve is really an assembly of very specific materials chosen for very specific reasons. So the body and the disc, the parts that take the most abuse from the flow, they're made from super tough, corrosion-resistant gunmetal or bronze. The stem is typically brass. The handwheel you touch, that's lightweight aluminum. And see that gland packing? That's PTFE, which you probably know better as Teflon, and it's there to create a perfect tight seal. Every single material is chosen to do a specific job.
And believe me, this specific choice of materials is no accident. Every single one is selected to deal with one of the most important and dangerous factors in any pipeline: immense pressure.
These materials have to be strong enough to hold back fluids that are under incredible force. And they have to do it without leaking and definitely without breaking. So to guarantee that, every single valve has to go through a super rigorous pressure test.
So just how much pressure are we talking about here? Well, the spec sheet gives us a number from its hydrostatic test, and that number is 15.
15? What, you're asking? That's 15 kilograms of force pressing down on every single square centimeter of the valve's inside surface. To put that in perspective, during the hydrostatic test, they fill the valve body with water and literally crank up the pressure to that level just to make sure it can handle that incredible force without failing. That number isn't just a spec, it's a guarantee of safety and reliability.
All right,
So now we know how it works, what it's made of, and just how strong it is. But here's the thing. Valves are not a one-size-fits-all solution. And when you're talking about industrial plumbing, believe me, size definitely matters.
So if you look at the external drawing here, you'll see these letters, A, B, and C. Now, those aren't just random. They actually correspond to a whole table of dimensions on the spec sheet. This is exactly how engineers know the precise physical size of every part of the valve, depending on the size of the pipe it's going to be attached to.
And check out the relationship between the pipe size and the valve size. It's pretty dramatic. For a little 1-inch pipe, the valve is about 170 millimeters tall, okay? But jump up to a 3-inch pipe, and suddenly the valve needs to be 260 millimeters. And for a big, major 6-inch pipeline, the valve itself stands a whopping 425 millimeters tall. It gets big fast.
And this chart just illustrates that relationship perfectly. As the pipe size gets bigger, the overall dimensions of the valve have to scale up dramatically, not just to fit, but to handle the larger volume and maintain its strength. I mean, look at that. You can just see the height shooting straight up.
And really, that's the key takeaway here. These super detailed specs make sure that whether you're dealing with a tiny half-inch pipe or a massive industrial main, there is a perfectly engineered valve designed specifically for that job. It's all about guaranteeing control at any scale.
So there you have it. We've gone from just a simple photo to a detailed blueprint. And we've decoded the mechanics, the materials, and the measurements of a globe valve. In a way, you can now read its story. So the final question I'll leave you with is this. Now that you know what you're looking for, where else in your world are these hidden controllers at work? If you start looking, I think you'll be surprised.